So let's start with our example. And as I said, number 1 is actually not really interesting. So we can start again with Rn. And our basis is the standard basis. So, and then you take U in Rn. And I think I have done this calculations, also this writing several times already. So U is U1 to Un. Now we can split this vector as usual as U1 times 1, 0, 0, 0 plus U2 times 0, 1, 0, 0, 0, and so on up to Un times 0, 0, 0, 1. And again, this is E1, E2, En. So we have U1, E1 plus dot, 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 Un, En. And that means these numbers, until now I always try. Yes. Oh. Yeah. Hello, yeah, you can say.
Sorry, Professor.
Oh, okay, okay. No problem. Yeah, but always ask. I mean, I think I'm also kind of quick. So yeah. So if you lose and fall behind, always let me tell you. Then I let me know. Then I can stop a little bit. Okay. So the vector which we usually write as a tuple of numbers can be written as U1 times E1 up to Un, En. So with our new definition, we get the same result like what we already said. Since we have Rn, we call these numbers also the coordinates of a vector. And it turns out what this means, it actually fits together with the definition we just made. Yeah. So that's always good. It means you define something, and for the old things which we know beforehand, it actually says, oh, it's actually how we expected this. And for sure, that's also how people came up with the definition, because they used vectors, and only later they realized, oh, what we are doing here can be actually generalized to different bases. No? So it turns out that's a good thing. It means this U1 to Un is really the coordinate vector of U with respect to the standard basis. So it was okay to call these coordinates. Usually we would not say standard basis, because remember in school they make it very kind of, they just say, oh, there's a picture, no? And then you say, oh, this, let's say here the coordinate system, and they say there's a point. How do we get to this point? 2 and 3. So it means drive 2 to the right, 3 up. So we write it as 2, 3, no? So it's kind of, they explain it in different ways. They explain it's a coordinate system. So you can go left and right, you can go up and down. And this is just how you drive from the origin to the point. No? But it's kind of tricky. In some sense, what they don't tell you, what this really means, we have one direction with this basis vector, the other direction with this basis vector, and it means this point is 2 times this vector plus 3 times this vector. Also, it's not a good thing to say this at the beginning. It makes things just too complicated. But keep in mind that perfectly agrees with what you have learned in school about the Cartesian coordinate system. No? There's one direction, there's another direction, and these numbers just mean how do you get from the origin to the point. No? Okay, so that fits with what you have learned before, and that's good. So it means it's nothing new. Okay, and the only trouble is, let's say, but usually people don't ask the question, what is actually special about this coordinate system? Why in the world would you not use this coordinate system? Okay, and then you're in trouble. I mean, your high school teacher's in trouble. No, why would we not use this? No, what is so special about this? Why does it have to have a 90-degree angle? And why is the x-axis always horizontal? Okay, there's actually no reason. No? Every coordinate system should be equal. No? It turns out that's the direction where we are going now. Linear algebra will help us to understand if you have different coordinate systems, what does actually change? Yeah. Okay, and as I said, it makes totally sense to start with this, so you learn all these things. But once you're really looking at it in the right way, you say, okay, why in the world would people, when they use this coordinate system, that should everything work in the same way? It turns out most of the things work in the same way. But that's one of the things which linear algebra can study. What's the influence of coordinate systems? And maybe that's not always the best coordinate system, no? Also, when I say that's not always the best, so what do I mean by this? Imagine you write a computer program which controls a plane, flying plane. The plane is in space and it rotates. So for the pilot, the coordinate system actually moves. For the pilot, it would be very confusing if you have a straight coordinate system. So if you write a computer program for a flying plane, and so that all the engines are running right and things like this, you have to move your coordinate systems if the plane goes into a turn, for example. So what the right coordinate system is really depends on what you're doing, no? And for sure, if it's only about plotting parabolas and cubic function and sine and cosine, okay, Cartesian coordinate system's fine, no? But in the moment you're going on a moving object, the right coordinate system is maybe not the coordinate system from the Cartesian coordinate system on the ground. Yeah. Okay, so that's kind of an idea. Why in the world would people look at other coordinate systems? Okay, I need to continue, not too many stories. Number 2 is, again, our polynomial space. So Pn is equal to a1x plus dot 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 anx to the power of n, where these are coefficients. And here, oh God, sorry, this morning I forgot everything. Okay. So now if you have a polynomial p of x, it can always be written like this. And we have the basis, which we just said in the previous example, is 1 x squared x to the power of n. Then we see these are just the coefficients. So if we call this basis s, then the coordinates of the polynomial p with respect to the basis s are these numbers. Yeah. So these numbers are the coordinates of your polynomial. And again, if you think about writing a computer program and you would like to store a parabola, what do you actually store? You store the coefficients, no? You store what is the constant, what is the coefficient in front of x, what is the coefficient in front of x squared. And that's exactly what this is. I mean, again, when you think about it, it's not so surprising, no? Okay, as I said, okay, hope that was not too fast. Now comes actually the most interesting part. It's what about these other bases in R3, which we just saw? How would we find the coordinates there? And again, the good thing is the calculation that comes up is nothing new. It's the same calculation we did since the first day of class. We solve a linear equation system. So this is now actually the most interesting. If you have never seen a basis and how do you find coordinates? So example number 3 is actually the one where we do really some calculation. So we have a basis S, which was 1, 2, 1. So that's the same basis we just figured out. That's actually a basis. And 3, 3, 4. And that's the basis of R3. And that's we just figured out in the previous example. So now the question is, if you have a vector u in R3, what are the coordinates with respect to S? So the question is, what is actually US? Sorry. what are the coordinates of u with respect to s? Okay, so the question is, if you have u and you write it as c1 v1 plus c2 v2 plus c3 v3, and these are the coordinates with respect to the standard basis, how do we find the coordinates with respect to the basis S? And okay, so again, what kind of question is this? Here we have U1, U2, U3. Here we have the coefficients C1, C2, C3, and we multiply C1 with V1. So again, the first column is the first column from here. Okay, sorry, this was V1. This is V2, like in the previous example. Now this is V3. So first column is 1, 2, 1. Second column is 2, 9, 0. Third column is 3, 3, 4. So we like to know this if we know this. So again, I call this matrix A, like I did before. So essentially, we like to solve this equation for this, which means we have to bring A to the other side. So that means C1, C2, C3 is A inverse times U1, U2, U3. So if you tell me the standard coordinates, you multiply it by A inverse and you get the coordinates with respect to S, where these are the columns of S. So it turns out this question requires the calculation of A inverse, which we have done often enough, but let's do it one more time. So we need A inverse, 1, 2, 1, 2, 9, 0, 3, 3, 4, sorry, oops, and then here 1, 0, 0, 0, 1, 0, 0, 0, 1. And again, our book, I think, made it pretty nice for us, so I don't think it's too complicated. So here we have to subtract 2 times row 1. Here you have to subtract 1 times row 1. At least that's how we can do it. So we get the first row is not changed. Now this minus 2 times this minus 2 times this is 5, this minus 2 times this is minus 3, 2 times this is minus 2, this minus this is 1, and then 1 times 0 minus 2, 1, this minus 1, 0, 1. Then we have to make a 1 here and eliminate this. So this equation I divide by 5, and this equation I add 2/5 of row 2. Hopefully I can do this also in my head. So we have 1, 2, 3, 1, 0, 0, 0, 1, minus 3/5, minus 2/5, 1/5, 0, 0, 0. And what do I do? 2/5 times this. So 1 is 5/5, minus 6/5 is minus 1/5. Minus 1 is minus 5/5. Minus 4/5 is minus 9/5. Then here is 2/5, and here is 1. Just give me a moment. I'd like to check in my notes. So also, if someone sees a mistake, please let me know. Okay, I think we are good. And so I turn this into 1. I multiply by -5. So we have 1, 2, 3, 1, 0, 0, 0, 1, negative 3/5, negative 2/5, 1/5, 0, 0, 0, 1, and this is minus 9. No, plus 9, minus 2, minus 5. Okay, now that's the Gauss part. We are at row echelon form. Now we reduce by putting 0, 0 here, minus 3 times row 3, plus 3/5 row 3. Again, 1, 2, 0, 1, 0, 0, and we already know this is 0, 0, and 1. Okay, so this minus 3 times this is minus 26. Here 6 and here 15. Then this plus 3/5 times this. So we have minus 2/5 plus 27/5 is 25/5 is 5. 1/5 minus 6/5 is minus 5/5 is minus 1. And that is just minus 3. And the last row is already done. And the last thing, we have to eliminate this. So we do minus 2 times row 2. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we have here this minus 2 times this is minus 36. This is 6 plus 2 is minus is 8. And 15 plus 6 is 21. And the other ones should be already fine. So I hope I got this right. Negative 36, 8, 21, 5. I think that's correct. So this here is our A inverse. So the coordinates with respect to S is you take A, which is the columns S, you take the inverse and multiply by U. Okay, so I hope you could follow this. Otherwise, I hope everyone would be able to find the inverse of this guy if I give you some time. Now, what does this mean? Now we do an example for this. First, again, with general coordinates, and then we plug in an example, just so you see what do we have actually now. So I copy this to the next page together with this formula. So the coordinates C1, C2, C3, which are the coordinates of U with respect to the new basis S, is A inverse. So I copy now A inverse from the previous papers. Negative 36, 8, 21, 5, negative 1, negative 3, 9, negative 2, negative 5, times the coordinates with respect to the standard basis. Yeah. So this is how we get the coordinates with respect to S if someone gives us the coordinates with respect to the standard basis. So now I make an example. In my example, let's assume someone gives me the vector 1, 1, 1. No? So this is the Cartesian coordinate vector. That means in the Cartesian coordinate, you go 1 to the right, 1 in the direction of Y, and 1 up. Usually C is up. No? So this is what this means. So this is a coordinate vector with respect to the Cartesian coordinates, or we can say the standard basis. Then we take this vector and multiply by A inverse. No? So A inverse times U is equal to, now we calculate this. So we multiply here by 1, 1, 1. So it's minus 36 plus 8 times 1 plus 21 times 1. 8 and 21 is 29. Minus 36 is negative 7. And again, 1, 1, 1 is this plus this, which is now 1. And then 1, 1, 1, this plus this is 9 minus 7 is 2. And that's the coordinate vector U with respect to the basis S. So that means the vector 1, 1, 1 is also the vector minus 7 times V1. Now we go back to the meaning of our basis. This is V1, V2, V3. So I copy V1, V2, V3, 1, 2, 1, plus 1 times 2, 9, 0, plus 2 times 3, 3, 4. So this is the meaning of the coordinates. No? And again, because of the standard, so it's also 1 times 1, 0, 0, plus 1 times 0, 1, 0, plus 1 times 0, 0, 1. Yeah. So these are the coordinates with respect to this basis, which we called S. 1, 1, 1 are the coordinates with respect to what we call the standard basis, or the basis which we usually use in the Cartesian coordinate system, right, down, and up. So that's here. And again, even naturally, we will always start with this, like I explained with the example of flying plane or anything else moving in space. It's not clear that these coordinates even make sense in space, because where is up and where is down? I mean, nobody knows this in general, no? Okay, so this is what you have seen now. If I give you different bases, you can find coordinates with respect to the basis, and finding coordinates usually means finding A inverse. Where, what is A? A is the matrix with the new basis as column vectors. So, like I said before, there are two new terms, basis and coordinates. How do we check for basis? We solve a linear equation system, or we check if the matrix has an inverse. Another new term is coordinates. Once we have a basis, how do we find the coordinates? Or we have to find the inverse of the matrix, or solve a linear equation system. No? Okay. So this finishes already chapter 4.4. And I like to prepare a little bit already, because at 10 o'clock, someone from the math lab will come. So I need to continue anyway until 10. So the next one, the next section is again where we introduce a new name. And most of the section is about that this name actually makes sense. The good thing for you is, I think, section 4.5, there is a pretty lengthy proof, which we will do. So that proof should show you, oh, it all makes sense, and it comes out exactly how we expected. The good thing about for you is actually, essentially, you only have to know what does dimension mean. And you will see in your homework question, for you on your side, I hope actually 4.5, even like I said, the proof is a little bit lengthy and take us some time. The good thing for you is essentially you only need to remember one thing: what do we call the dimension? And so that's, I hope, a little bit an easier section.